Hi.
Yeah.
Hi. Good morning, everyone. Welcome to the third and final day of Bqit 2019. It's my absolute pleasure to be able to chair this session. We've got a fantastic lineup of speakers. So to kick things off, we've got David Elkouss from Delft, who's going to talk about the quantum internet.
Okay. Can you hear me? Okay, so first of all, I would like to thank you for the invitation. It's a great pleasure to be back in Bristol. So I would like to tell you a little bit about our efforts towards the future quantum internet. So what will be this future quantum internet? Our vision is that this will be a global network where in each of the nodes there will sit some quantum information processing device, and the quantum information processing devices will be linked by quantum channels. And in this way, arbitrary points in the globe will be able to exchange quantum information. So please remark the words vision and future. Okay. So we are very excited because we believe that we are in a very special moment in time, analog to the early days of the internet that we know today. So let me make this analogy very explicit. So let's go back to the 1960s. So then ARPA was decided to connect the different mainframes that it was funding in American universities. And after 2 years of work, there was some prototype between 4 universities in the state, and they were ready for, let's say, alpha test. So this is I'm going to present the log of what happened that day. So on UCLA, there said Charlie Klein, a student programmer, a PhD student, and on Stanford there was Bill Duval, and this is what happened that day. So at UCLA, then they were trying to send the word login to the other side of the line. They typed the letter L, and of course, since this was an alpha test, they needed some means to verify what was happening, some external means, so they were also connected by some telephone line. And they said, we've typed the L, do you see the L? And then Stanford said, yes, we see the L. So then they typed the letter O, and they said, Stanford, do you see O? Yes, we see the O. And then they typed letter G, and the system crashed. So, I mean, this is very embryonary, but it's already highly non-trivial. So we believe that we are close to being able to send quantum login. Okay, so before going into a little bit more of detail on the quantum internet, let's review the state of the art of quantum communications. So this situation is a little bit different depending if we talk about free space communications or fiber optical communications. So if we talk about the free space, then definitely the state of the art was shaped by a series of experiments performed by the PAN group in 2017, and most notably they were able to distribute post-selected entanglement over a distance larger than 1,200 kilometers. Now, if we talk about fiber optical communications, most of the efforts in the application of communication protocols have been focused on direct transmission quantum key distribution. So what's the state of the art? There are a number of commercial companies that have been pursuing this technology, and notably a few of these companies also allow to directly buy equipment. So if one wants to distribute keys between some short distance, then one can call one of these companies and buy equipment. So with this commercial equipment, perhaps we can go roughly, I don't know, 100 kilometers. With lab equipment, I believe the state of the art is some recent experiment by the Geneva group where they managed to do quantum key distribution over a distance of 420 kilometers. And the grand challenge is to go to very long distances. Of course, if we talk about direct transmission, this is not really possible for fundamental reasons, basically because the transmissivity scales exponentially with the distance. So up to 2 months ago, this would have been the end of the slide. But there has been some very recent exciting development on proof of principle functional repeater experiments. What do I call a functional repeater? This is some device that one places between the 2 nodes. And with this device, one is able to achieve a rate for some communication task that is strictly larger than the best thing that one could do without the device. That is, that one can achieve a rate that is larger than the capacity. Capacity was described in great detail in the presentations yesterday from Rubino and White. And most notably, so all these 3 experiments bit capacity in some regime. The one in the bottom achieves some non-negligible rates with 90 dBs of losses, that if we translate this to ultra-low loss fiber, this would mean that one could achieve some non-negligible rate over a distance of, let's say, 550 kilometers, well above the current record with direct transmission. So there has also been efforts implementing some other protocols, mostly quantum crypto. Most of them have been also proof of principle implementations, but some of these protocols share the same hardware requirements as prepare and measure QKD, so there's no reason in principle to believe that they could not be taken to this stage also. Okay, so these are really breakthrough experiments, but they are not truly scalable. So until we have scalable quantum repeater solutions, what has been the solution? So if one wants to distribute keys over a very long distance, there has been this concept called trusted repeater networks. It's called network, but in fact it only works for quantum key distribution, and it allows to distribute keys under some requirements or hypotheses. So let me explain the concept. It's very simple. So let's suppose that Leia and Luke want to establish some secret key, but with some quantum key distribution system. But unfortunately, they are at a distance longer than the reach of their equipment. So then they are going to use the help of some third party. And then what Leia is going to do, she's going to distribute some key via quantum key distribution with a third party, and the third party is also going to distribute a key with Luke, and then the third party is going to publish the sum of the two keys. So if the third party is trusted, then Leia and Luke obtain a secret key. But of course, we need to trust the third party, and that's not always the case, right? So this concept has been pushed over the last almost 20 years, and there has been some very impressive networks deployed. Two of the most famous ones are this one in Japan here, and this one in China. This one in China covers a distance of roughly 2,000 kilometers, and it has close to 100 nodes. I believe this is expanding, so maybe this is not accurate anymore. Okay, so what we want to do in QTech is to go beyond this point-to-point quantum key distribution and beyond these trusted repeater networks, and we want to make a demonstration in 2020 where non-adjacent nodes in a, well, this is national, but we could call it metropolitan network. The Netherlands is very small. Can distribute entanglement. And also, we will implement some quantum network stack in such a way that physics experiments of heralded entanglement are turned into a resource that allows to program the network in a platform-independent way. Okay, so when one hears these very ambitious goals, there are many, many questions that come to mind. So before I proceed, as sort of a disclaimer, I will very briefly review the internet efforts in QTech. So these internet efforts are part of a roadmap in QTech called Quantum Internet and Network Quantum Computation. This is one of the 3 research roadmaps in QTech. There are 6 research groups, 3 experimental groups, one led by Tim Taminiao working with NV centers. He's mostly focusing on quantum computation. Then there's the group of Ronald Hanson. He's focusing more on communication protocols. Wolfgang Tittel works on quantum key distribution and also on quantum repeaters. Then we have a true theoretical physicist. He's Slava Dobrovitsky. At least in the context of quantum internet, he's working on the physics of NV centers. And then there's the groups of Stephanie Wiener and myself that have more of a, let's say, computer science flavor. So this is also a disclaimer that the questions that I'm going to find relevant and I'm going to address in the rest of the presentation will have a little bit of this CS or networks flavor. Okay, so what are these questions that I'm interested in? So this is some mixed meetings that we hold regularly between experimentalists and theorists, and they go better than one would expect. So there's really communication here. Okay, so what are these questions? So I think that perhaps one of the most relevant questions is, let's assume that in 2020 we have built this demo network, and one can distribute entanglement between non-adjacent nodes. There's also this quantum stack. and we can implement not only quantum key distribution, but a few other communication tasks. So then the question is this the quantum internet? So certainly this is more than a trusted repeater network, and it allows to implement more things than key distribution, but there will be many other protocols or tasks that will not be within reach. For instance, we will not be able to do distributed quantum computation with gates below threshold, right? So there's many protocols that will not be within reach. Is this a quantum internet or is it not? So I'm going to give a little bit away the answer. We are going to propose a set of stages that classify the quantum internet depending on the functionality available to the nodes. So then the second question comes from these stages. So, okay, so there's this set of stages, and we sort of feel that the functionality available to the nodes is X. So can we really guarantee that we have achieved this functionality or not? How can we certify the states we are in this quantum internet? And the third question I want to address has a little bit of a different flavor. So again, let's suppose that this demo or some other network is a success, and now we want to scale to some pan-European network with 1,000 of nodes, and there are some architecture for the network that we feel is going to be very successful, and there's some quantum network stack that we also think is going to be great. Then how do we predict the rates at which we are going, for instance, to distribute entanglement over this network, and what is going to be the fidelity of those entangled pairs that we are going to distribute? So this might seem like a not so pressing question as these two, but somehow if we cannot predict what's going to be the behavior of a large network, then definitely we are not going to convince the world that we need the resources to implement it. So I think this is also a very, very pressing question. Okay, so I'll begin with the first one. What have we achieved? So now, before I continue, let me introduce some elements of the quantum internet. For the purpose of this presentation, this will be enough. So we'll have the end nodes. And these end nodes can have very different capabilities. So maybe they allow to prepare some qubits, maybe they allow to measure qubits, maybe they allow to store qubits for a certain amount of time, maybe they also allow to manipulate qubits, and this manipulation might be extremely noisy or might be below some fault-tolerant threshold. Then end nodes will be connected by quantum channels, and every now and then we will place repeaters to bridge distance whenever losses are too high. So for this presentation, this should be enough. Okay. Also, so a question I should have posed at the very beginning is, why do we want to build this quantum internet, right? So it's going for sure to be a tremendous endeavor, but extremely challenging. So why would we want to build it? Maybe the answer is basic physics, but maybe the basic physics we already observe with small networks. So why go for a global quantum internet? So the answer is very simple. We believe it's going to be extremely useful. And then, since it's going to be very useful, we decided to classify stages of a quantum internet depending on this usefulness of the network. And in order to capture this usefulness, we decided to propose the stages depending on the functionality, the network functionality available to the end nodes. So before I go into detail with each of the stages, we see that we have on the very bottom trusted repeater networks. This should be something like state 0. It's not completely quantum because there's no quantum information going from end to end of the network, but it achieves some quantum features, so it's fair to have it in this list of stages. And at the very top, we have what we call quantum computer networks. Here we have a full-fledged quantum computer sitting on each of the nodes. And there's a series of intermediate stages until we are reached the final holy grail. Okay. So now to the stages. The first stage we call prepare and measure networks. So we say that a network has achieved this first state if for any pair of nodes in the network and any qubit state and any projective measurement, there exists some way for node I to prepare the qubit state phi and transfer it to node J such that one of two things happen. Either node J can perform the measurement M on the state, or node J can conclude that the state was lost. So I guess you can quickly see that this functionality is clearly inspired by prepare and measure quantum key distribution. So what are the protocols that are feasible within this stage with this functionality. So of course, prepare and measure quantum key distribution, two-party secure function evaluation in the noisy storage model, secure identification, position verification, and some very rough protocols for coin flipping. A word of caution, this functionality does not imply that it's possible to transmit arbitrary qubits from node I to J. Okay, now the second stage we call entanglement distribution networks. So what's the additional functionality that all nodes need to fulfill? So we say that we are in this stage if on top of the functionality available on stage 1, for any pair of nodes I and J, the network supports the creation of an EPR pair, and there exists a way to deterministically perform a single qubit measurement at each of the two sides. So what protocols become available with this extra functionality? Basically the device-independent versions of the protocols in the prepare and measure stage. On stage 3, we introduce memory. We call these quantum memory networks. So the functionality, the extra functionality that we require here is that for any pair of nodes in the network supports the following tasks. It is possible to prepare ancilla qubits. It is possible to measure a set of qubits in one node. And it is possible to apply arbitrary unitary within this node. I'm not saying anything about the precision of these operations yet. And we say that the quantum memory network is k-bound if the storage time at the node is larger than k times t, where t is the maximum time that it takes to send classical information from one node in the network to another node in the network. What protocols can we do in this stage? We can do deterministic teleportation, that is and we can then teleport unknown states. New set of crypto protocols become feasible. For instance, secret sharing, some better coin flipping protocols, anonymous transmission of quantum states, some simple leader election protocols, and blind quantum computation in the case that there's some node in the network that is a very powerful quantum computer. So this is different to the capabilities of the network. The network would enable blind quantum computation, but whether or not there's a quantum computer that is accessible from the network, that's a different story. Okay, so these 3 stages are what we believe that is going to be feasible in the near future. So one thing I forgot to tell is that we've somehow thought of these stages, thinking on the usefulness of the network, but one, let's call it, feature of this sort of classification is that the same kind of technology, so let's fix some technology for doing quantum networks, and then let's now build some small quantum network. Then maybe it achieves a certain stage. And this very same technology, if now we try to build a very large network, might achieve a lower stage, right? This is somehow a consequence of how we've decided to construct these stages. Okay, so this is an aside. So up to here is what we believe we are going to be able to do in the near future. This 2020 network should be a quantum memory network. Then we have 2 more advanced stages. We have a few qubit fault tolerant network, and we call network in this stage if the gates are below some fault tolerant threshold, and if it has at most a certain number of qubits, and this number we fix from what can be simulated classically. So with this functionality, we can do a new set of protocols, in concrete some clock synchronization protocols, distributed quantum computation. And in the final stage, we have quantum computing networks where we have a quantum computer sitting on each of the nodes. And then there's a new set of protocols that become feasible, such as some very sophisticated leader election protocols, some fast Byzantine agreement protocols, or perhaps some sophisticated fingerprinting schemes. Okay, so this is a a brief, sorry. A brief description of the stages. Okay. So the second question is, how do we verify that it worked? So the answer is very simple. We can stack goodness tests. So let me recall what's the trace distance operationally. So we have some ideal state rho, and that we want to implement, but instead, in reality, we have some state rho tilde. So then the trace distance between rho and rho tilde measures how well these two states can be distinguished. And it has a very concrete operational meaning in the sense that if we now use the rho tilde instead of rho in some protocol, then the error in the protocol that is using rho tilde instead of rho can never be larger than the trace distance. So we can lift this definition to distance between processes. So now let's suppose we have some ideal process that we want to implement, but instead in practice we have some real process that we have implemented. So we can estimate the diamond norm distance or diamond norm or diamond distance, was under different names, which is the maximum over the output when we optimize over all input states into the ideal process together with some ancilla. So we compute the trace distance optimized over this set, and this will give us the diamond distance. So this carries the same operational meaning as trace distance, and basically we have a protocol that is composed of, let's say, 3 operations, and instead of these 3 ideal operations, we implement 3 real operations, each with some error bounded by epsilon. This means that the total error of the protocol cannot be larger than 3 times epsilon. So let's make this more concrete. So let's go to the first stage, prepare and measure networks. So here, if we characterize the goodness of the transmission channels and of the measurements in terms of this diamond distance, and the sum of these two is upper bounded by 0.11, then suddenly we can implement all the known protocols in this stage. Okay. So now the third and last question I want to address, how do we predict performance? So let's consider the demo network, and let's assume that, for instance, we want to distribute entanglement between Delft and Leiden via, I don't know, Amsterdam. And then we think, so we have the hardware, this is going to be NV centers, and we are going to try to distribute entanglement according to a certain logic. Perhaps, so we are going to do single-click protocol between Delft and Amsterdam, and Leiden and Amsterdam, and then depending on the time it takes to achieve the second pair after we've achieved the first one, we will distill or we will discard, we can take a certain number of decisions. So if we want to analyze this protocol, then we need to take into account several things. So first, all these processes are going to be non-ideal, so the preparation is going to be noisy, that might be noise in the channels. Communication, both quantum and classical, is going to take a certain time. And perhaps most important, induced by this noise, we are going to have that the events are stochastic. So that means from the entanglement generation that we are going to try many times until we succeed, to the distillation, which might succeed or not. And then depending on these events, we are going to take different decisions. So this is a very simple setup. And if we think of a concrete protocol, then maybe we can get away by modeling everything, even on paper, maybe on some mathematical notebook. But what should be clear is that this gets very complicated very soon. So as soon as we go from this toy example to a slightly longer repeater chain, then analytics is completely out of reach. And even doing an ad hoc simulation on MATLAB or Mathematica is going to be extremely time consuming. So what can we do? We can simplify the problem. So we can assume that noise is of a very simple way. Maybe gates take no time, a certain number of assumptions, and then we can predict behavior. Or we could do something similar with the numerics. But the thing is that if we simplify the model, then suddenly the predictions don't need to translate to reality, right? So we are predicting things in a very idealized model, and we don't really know if they are going to translate or not to reality. So this problem I'm describing has nothing to do with quantum. It's the same problem, basically, that people in classical networks have been facing for, I don't know, 40 years. And the solution comes in this paradigm called of discrete event network simulation. So let me quickly brief you on this concept. It's very simple. So At the beginning, what this simulator does, it initializes some global clock to 0, then initializes some network state, some hardware setup, and initialize a set of events that are going to take place in the future according to the protocol that we want to implement. Then there will be some main routine, and it will move the clock to the next event in the line. It will call some routine that will implement that event, and it will update the network state according to the event that happened. Perhaps it's also going to update the list of events that are going to take in the future. It's also going to log certain parameters that we want to track. I don't know, fidelity of some state or something like this. So this is repeated many times until we reach some termination condition, and then we generate some simulation report of the tracked items, and we finish. So if we want to have a powerful network simulator, then there are two things. First, we need to build such an engine that is very efficient. And the second very important thing is also that we need to build some library of hardware models and also of base protocols in such a way that if we now want to simulate some new protocol, the only thing that we need to do is to describe the connectivity of the network, the underlying hardware, and the new protocol as a function of the already known protocols. And yeah, so this has been the way that people in the network community predict the performance of classical networks. So unfortunately, not such a thing existed for quantum information, so we have built in-house a discrete event simulator for quantum networks called netsquid, which I always forget is network simulator for quantum information with discrete events. So we basically swap the things such that we have some nice title and we have some nice logo. So it accepts multiple formalisms, get, density matrices, stabilizer states. We do the same thing that the classical network simulators do. So if we need to deal with stochastic processes, so basically we throw coins and we take statistics. We've implemented some library of base protocols and hardware, and there's this sort of separation that allows us to describe protocols in a moderately easy way. And depending on the level of detail in the description of the simulation, we can already simulate up to 1,000 nodes. So we are currently on version 0.5. This means there's still some rough edges, and we expect to release 1.0 by the end of the year. So while this is extremely useful and relevant for the future of quantum networks, is in some way also an obvious idea that takes lots of effort to implement, but an obvious idea. And this means that there are other people that are trying to pursue the same idea. So we learned recently of Argonne Labs sequence. It also has not been released yet. It was presented in the March meeting. It stands for Simulator of Quantum Network Communication. And I believe there's also several other groups trying to pursue this line of work. This is an outdated list of the active collaborators in netsquid. The list has grown heavily. Okay. So here we have a cartoon picture of how would one program a concrete protocol for the demo network. So let's suppose now that we want to distribute entanglement between, as I said, Amsterdam and Leiden, Delft and Leiden. And then we will have the NV centers. We would say that they are going to distribute entanglement according to some, so they will be connected via some beam splitter. We will have some generic template for these NV centers, and we would need to fill in the concrete noise parameters that we want to apply. And this could be on the static hardware level. And then on the level of the protocol, we might want to do some distillation, and we could construct it from Barrett and Conk scheme, which in turn can be constructed from doing twice some single-click entanglement generation scheme. And then if we then want to use the entanglement for something, let's say for teleportation, we could build the teleportation on top of all these schemes. This kind of structure, you can see, is very flexible because we have NV centers here, but we could have some other hardware if we want with very little modification of the top protocols. Okay, so here we have some example data. This was presented recently by Tim Koopmans, a student of my group in the March meeting. So here we want to understand the behavior of long repeater chains. So here long is 9, but we want to understand the longer chains. So at each node we have an NV center, and the NV center has been modeled very accurately, but we now want, for instance, to understand what's the sensitivity to certain concrete parameters. And then what we are going to do is we are going to take all the noise parameters to noiseless except for one. And what we are going to have is where we have the point 1.0 means that the concrete parameter, here we are tracking the probability of double excitation and photon indistinguishability. We are going to have here state of the art, and we are going to interpolate to completely noiseless. And in this way, we can see what parameter would be more interesting to optimize. So this is, this is real data, but we are doing a more systematic study of the problem. So beyond this concrete problem, we want to use netsquid to simulate large quantum networks. So within the context of the Quantum Internet Alliance, we are currently modeling the different hardware components from the teams in the Quantum Internet Alliance. For instance, we are modeling the ion traps that we heard of on Monday, and also atomic ensembles. And we will be implementing several concrete use cases such that by the end of the project, we can test different sets of protocols and architectures with different hardware to understand what combinations are more promising, and also to indicate in the way that I showed in the previous slide what parameters are more useful to improve. Okay, so let me quickly recap. So I posed a set of 3 questions regarding this future of quantum internet. So what have we achieved? And in order to answer this, I propose a series of stages for the quantum internet. These stages are driven by the functionality available to the end node. And there are some very concrete open questions. So associated with each of the stages, we did put some task, but we did put some task because the simpler protocol that we know sits in that stage. But there's no reason why there could not be other protocols that allows us to achieve the task at a lower stage. So the open question is, what is the least amount of resources, the lowest stage where we can put the different communication tasks? And another very relevant question is, I said, okay, so we can certify that we're in a certain stage by stacking goodness tests. But of course, these goodness tests are very complicated to perform in experiment, that they can be performed, but they are very resource demanding. So the open question is, we can find some nice integrated test that allows us to guarantee that we are in a certain stage. And finally, I posed the question, so how can we predict the performance of large quantum networks? And I've described our efforts with some discrete event quantum network simulator called the netsquid that already allows to predict the performance of medium-sized networks, and very soon of large quantum networks. So before I conclude, some publicity. So if you want to send quantum login in 2020, please join us. We have a number of opportunities for master students, PhD, and postdocs. And this is the people involved currently in the network simulation effort. So thank you very much.
Thank you very much for the talk, David. That was really excellent. Do we have any questions? Alistair.
Hello. This 2021 quantum network simulation, is that using a classical network to simulate a quantum network, or is it all simulated just on a single computer?
So we will be simulating using this netsquid simulator I described. Depends on the size of the network, you can do a simulation on your own computer. That's possible, but for very large networks, we foresee the need to use a supercomputer. In concrete, we are working with Surfsara's, which is one of the largest supercomputers in the Netherlands.
Thank you.
Is there a question to Roberto?
Have you had a chance to involve some of the people in the comms industry or in the standards bodies like ETSI, just to sort of help you in the certification and prediction processes?
Is this related to how do we understand that quantum networks are going to evolve?
No, just you've identified some really good approaches to going towards a quantum internet. Have you involved any of the standards bodies like ETSI or any of the industry players, big industry players, to help you validate what you're doing, the approach, and how well would it be received by industry in the future, the communications industry, let's say?
So QTech is in contact with ETSI different standardization bodies, but I'm not sure that these stages have been discussed in that context. Yeah.
I just have, Josh has a question. And Sewu.
Thank you, interesting talk. It's easy to imagine perhaps linking together nodes using QKD and allowing people to, run their cryptography over such a network of this size. It's quite a different question or a different problem to imagine running a distributed quantum computation or something over links which I can't imagine will ever reach the kind of loss levels required. Can you comment on that?
Well, in my view, a distributed quantum computer is a large quantum network on a tabletop, right? Yeah, I guess a priori it's difficult to indeed foresee single quantum computer being in a completely distributed fashion over a large distance. I agree with you. Yeah.
So I have a somewhat detailed question. So can you use the netsquid framework to make estimates of the required device performance you need in terms of a threshold to sustain some kind of link at some fidelity and things like that? Is that another thing you could do?
That's exactly what we have in mind. Yes.
Oh, okay. All right. How far? Is the code going to be publicly available soon?
That's a tricky question because of European funding. So we are not sure. We are currently drafting the license. I really don't know what's going to happen.
Great. If there are no more questions, let's thank David again for his talk.